Okay, let's start with functions. Now, functions is the chapter which I think is it's conceptually and algebraically also pretty straightforward, but because there's a lot of algebra involved, in my opinion, a lot of the students miss the big picture of functions or why do we really need it, right? So, functions up is explanation maybe a bigger chapter, so this video will probably not cover all of it. I will probably talk about what functions are, why do we need them, etc. Like just the intro, right? The different types of functions. I'll talk about the concept of domain and range, and also inverses, right? This is probably what will be it for this video, right? And what would be left would be quadratics, and that's a big part because in your exams, a lot of the questions are from quadratics. Secondly, modic functions, right? These are also fairly important. And what's the most important, in my opinion, is are the composite functions, right? And understanding how composite functions work is pretty important. Right, so let's kick off with what functions are. So if you're a computer science student, you probably know what functions are, right? But even for the average layman, functions is something along the idea that you do something, right? You give some input, right? The function does something to it, and it spits out an output, right? And this is basically what it is. The function takes an input, it does something to it, and it gives out an output. So when we write y equals 2x plus 3, right? And for the time being, let me just tell you that x is an element of all real values. Right? This is what's called the domain. I will talk about this later, but for the time being, what I'm basically saying is that this value x, it can be anywhere on the number line from 0 to all the way you can go to the right and all the way you can go to the left. It can be any number, right? X can be any number. It can be -1, it can be negative half, it can be 1, it can be pi. Right. So x is a variable over here, right? We are defining the output y, what the y value is the output, right? We are inputting some value x, and what we are doing to that value, will multiplying that by 2, and whatever answer that gives us, we're adding 3 to it, and whatever answer we get is the value of y. That's the output. So here, the output is y, the input is x, and this whole, let me change the color, and this whole is our function, right? Since we are defining y in terms of x, y is a function of x, right? And f of x is basically 2x plus 3. What we're saying is, no, whatever x is, what you do is you take that input, you multiply it by 2, and then you add 3 to it. So, for example, if I say what is f of 1, it would be just replace x with 1, right? This would be 2 plus 3, 5. If I say what's f of 2, it would be 2 times 2 plus 3, which is 7, right? So when you draw your graphs, let me just make a rough drawing of 2x plus 3. 2x plus 3 looks something like this, right? So on the x-axis, these are all your inputs, right? These are all your inputs. And this y-axis, these are all your outputs. So y is the output, x is the input, right? And what this basically means is that when x is of this value, right? When x is of this value, the output is this certain value of x. So for example, when x is 1, the output the function will give would be 5. When x is 2, the output the function gives will be 7. And this line you could call, this is like the function. It is giving, if it is giving you the value for every x, right? What would be the value of y when you input x, such like this? What will be the value when you input it like this? Right? And this is the big idea about functions. This is it, that you give some input, it does something to it, and you get the output. And we're defining y in terms of x. We're defining y in terms of x because this is the input and y would be the output. Right. So these are functions. Right. Now let us look at the different types of functions there are. Let me draw a graph. Okay. Now, I just gave you the example of 2x plus 3. It is called a linear function. And in a linear function, is when it's a line, let me draw a list of inputs over here, right? The inputs go through the function, and these are the outputs, right? So when I input 1 into it, it gives me the value 5. When I input 2 into it, it gives me the value 7. When I input 3 into it, it gives me the value 9. Right? So graphically, what this means that at this value, x is 1, y is 5. And such a function which whose output has only one unique input to it, we call this function a one-to-one function. And what this means is that basically, if you have this output 9, 9 can only be achieved when you input 3 into it and no other value. There won't be any other value. Let me draw the arrow going towards there. There won't be any other value x, which if you input into the function, it will also give you 9, right? So basically, it is a one-to-one function if there's only one arrow pointing to the output, right? One went to 5, two went to 7, three went to 9, and there's only one arrow that is pointing towards 5, 7, and 9, right? Let me give you another example. Let me take a classic quadratic, right? We'll cover quadratic in detail later, but for the time being, this is y equals x squared, right? Now let's take our inputs. It will go through the function x squared. Let me take out some outputs. Right. So when I input 1 into it, what output does it give me? So y equals 1 squared, it gives me 1. It gives me 1. When I input negative 1, what does it give me? It gives me 1 again. So negative 1 and 1 both go to the same output 1. To give you another example, if I input 2 and minus 2, both of them would go to 4. Right. So here you see that to only one single output, there are two arrows pointing to it. Or in a more meaningful way, for one input, for one output, there are two inputs. Right. You can input two separate values and it would give you the same output. Right. And when you have such a condition, we call this a two-to-one function. And you can probably draw the relation that as the number of arrows over here would increase, this would increase likewise. So just to convince yourself that you've got it down, just to see if you've got it down, convince yourself which function would this be. I'll just tell you that this is a 3-to-1 function, but just question yourself why that is the case, right? So whatever I've done over here and here, it would be summarized with the horizontal line test. Right? Now what the horizontal line test is that if you drop a horizontal line in the graph, right? It is a function which basically you want it to intersect at the maximum points it can. So let me take this graph over here. If I drop a horizontal line over here, it intersects at 1, 2, 3 points. So this is a 3-to-1 function. If I drop a horizontal line over here, this will be a 2-to-1 function. If I drop a horizontal line here, it will be a 1-to-1 function, right? And just so that you know the intuition behind it, for example, if this is the value of y1, y will be 1 when x is both negative 1 and 1, right? If I take the value of y as 4, when y is 4, the x value can either be negative 2 or it can also be 2, right? And the last type of graph, which is not really a function, is what maybe some students get confused. And so, for example, if I gave you, let's take y squared is equal x, right? So y is root x and negative root x. And the graph looks something like this. Let me draw a bit neater graph. Looks something like this, like this. Okay, so let's draw our basic structure again of inputs and outputs. These are the inputs, these are the outputs, right? So when the output is, let's take, when x is 4, y is either 2 or negative 2, right? Because it's either positive root x or negative root x. When it's 9, it's either 3 or negative 3. And the graphical meaning of this is that when x is 4, these are the two values of y, negative 2 and 2. When x is 9, these are the two values of y, negative 3 and 3. So for the same input, let me change color. For the same input, you're getting two different outputs, and this is why this is not considered a function at all. This is not a function, right? And maybe to draw some analogy that might help you remember, think of the function as some vending machine, right? This is our vending machine. Let's call it a function, right? And there are keys over here: 1, 2, 3, 4, 5, 6, 7, 8, 9, right? All the way till 9. And you put your money in here. So the vending machine is such that, for example, when I press 1, it gives me cola, let's say. And when I press 4, it gives me, let's say, it gives me Lays, right? When I'm pressing keys, I'm basically giving the function an input, and it is giving me out a product, an output, right? So the function is such a vending machine that if I press two different keys over here and it gives me the same output, it is completely fine, because I will still have to pay every time. I will still have to insert a coin over here every time I press a key. So for example, if pressing 1 and then inserting a coin gave me cola, and pressing a 7 and inserting a coin also gave me cola, it is completely fine because I still have to insert a coin. So two different keys can give me the same product and it will be completely fine. What would not be fine if, let's say, I press 2 and it gave me two different products at the same time. So for example, if I pressed 5 over here and it gave me Sprite and it also gave me Cheetos, right? This is not acceptable because you're inserting only one coin and you're getting two different products for the same price. So this was just an analogy that would maybe help you remember that this is not a function, right? And to test whether something is a function or not, like we did for the category, for the category we did the horizontal line test. To test whether a graph is a function or not, we do the vertical line test. So for example, if I gave you something like this, right? I will drop a vertical line such that it intersects the curve at most points, right? And here we see that oops, my alarm went off. We see that it intersects at 3 points, hence it is not a function. For it to be a function, it must only intersect at 1 point, because one input, one value of x should only give one output for it to be a function. So for example, if I drop a vertical line here, it intersects at 2 points, hence it is not a function, right? Anywhere I drop a vertical line here, it will always have only one intersection. Same goes for this, only one intersection. Same goes for this, only a one intersection, right? So this is how you check whether it is a function or not. Vertical line test is to check whether it is a function or not, and horizontal line test to check what type of a function it is, right? So this was for functions. Now, if I go back up here, I told you that X is all real values, and I told you that this is what's called the domain. But I didn't but I didn't dive deeper into it. So this is what's called the domain, and this is what I will talk right now about. Right. So let's talk about domain and range. Let me zoom in a bit. Right. So domain and range. Okay. So let's say, please draw a straight line. Better. So let's say there's some graph y equals 2x, right? Y equals 2x plus 3, right? And if I do not restrict the input I give to it, right? Let's say this is the x-axis, and let's say that inputs are all real values. What this means is that for any x on the number line, for any value, there will be some output, right? So if I were to draw a number line over here, these are your inputs: 0, 1, 2, -1, right? And this is your output: 0, right? And this goes through the function. So for example, if I input 1 into it, 1 goes to 5. If I input 2 into it, 2 goes to 7. If I input 0 into it, 0 goes to 3. Right? So if I do not restrict the number of inputs I give to it, there will always be some more outputs, and the graph will keep on stretching above and below. However, if I told you that, let's say that the domain of this function d is somewhere between, let's say, 1 to 4 inclusive, right? And this is just a formal way of writing 1 and 4, right? 1 to 4, because you can break this up into two parts, and what you're saying is that x is less than equal to 1 and x is greater than equal to 4. So on a number line, this looks something like this, all the values between 1 and 4, right? And whenever you're describing a range, you tell the extreme values, right? You tell the lower limit and the upper limit. So for example, if there's a roller coaster ride, and I want to restrict the ages from 14 to 30 only inclusive, right? So I want ages A to be greater than equal to 14, and I want ages to be less than equal to 30. So I can write this as 14 is less than equal to A is less than equal to 30. And I'm defining the upper and lower limit, right? I'm telling you the extreme values, and this is how you tell ranges, right? So what domain really is, it is the ranges of input that the function can take. So here the function can take all the values from 1 to 4. So at 1, at when x is 1, the output would be 5. When x is 4, the output would be 2 times 4, 8 plus 3, 11, right? So if I'm restricting my domain to only these values of x, my graph will also be restricted, and it will look something like this, right? It will look something like this, just the red part, right? And what ranges are just the range of values of the outputs, right? So here, the lowest value you get is 5, and the maximum value you get is 11. So your range of this function for this certain domain would be 5 is less than equal to f of x, which is just y, the outputs, which is less than equal to 11. Just saying that the ranges of output you get are between the values 5 to 11 for when you restrict the domain from 1 to 4, right? That's the concept of domain and range, and maybe it won't seem that useful or relevant right now because we haven't done quadratics. But when we come to quadratics, you'll probably see why it's helpful, why we need to do it in some cases. All right, so this is done. And the next bit I would like to jump to is actually inverses, right? Inverses. So what are inverses? Well, inverses, inverting something, doing the opposite, right? So An inverse function is similar. An inverse function f inverse of x basically undoes undoes what a function has already done, right? And let me explain what I mean by that. So let's say this is some input, right? Okay, some output. So let's say there was some input 2, and after going through a function f of x, it became 5, right? You took 2, you inserted into f of x, and it gave you 5. Now, what f inverse of x will do, it will take this 5 and it will give you back 2. It will take this 5 and it will give you back 2. So let's note something down. X comma y, right? Here the input x, the x values were the input. So here the input was 2 and the output it gave was 5. Here you're taking 5 as the input, right? You're inputting 5 into the inverse function. So 5 is actually the input and 2 is your output. You'll notice that the inputs and the outputs have swapped their places. And this is what happens in an inverse. If your function, if y equals fx has the coordinates x comma y, then f inverse will have the coordinates y comma x. And this is the reason why, because you're taking the output, you're inputting it into the function inverse function, and it is giving you back the input, right? What this looks in a number line. So let's say these are your inputs, right? Let me draw with a different color. These, let's call it f of x, right? This is you inputted f of you inputted these values into f of x, and okay, let's just call this first, and let's call this second, right? So I have a bunch of inputs, let's say 0, 1, 2, and I am taking these inputs, I am inserting it into f of x, right? So 1 goes to 3, sorry, 0 goes to 3, 1 goes to 5, 2 goes to 7. All right. Now, if I put these values in f inverse, what they will do is they will have the opposite effect. They will take 7 and they will give me back 2. They will take 5, they will give me back 1. They will take 3, they will give me back 0. Right? This is the effect of f inverse of x. Right? So now that you know what f inverse of x is, the purpose of, let's look at the more technical side of things, right? How, first of all, how do you find inverse? Second of all, how do you sketch inverses? And thirdly, I'll go a bit deeper into why this makes sense. And if you're not that interested into it, you may leave that part. You can completely make do without that part. You can solve questions, but if you want the understanding, that might help, right? So first, let's look at how do you find inverses. So if I have any value y equals 2x plus 3, the way you find inverses is first you make x the subject. Making x the subject basically means x equals to something something, right? And you could think of it as making x equals a function of y, right? So let's make x the subject. Y minus 3 is equal to 2x. X would be y minus 3 over 2, right? Now that you have this, what you do is you swap the x with y. So your final answer would be that f inverse of x is actually x minus 3 over 2. And this is your f inverse of x, and this is how you find inverses. Number two, how do you sketch inverses? Well, let's just draw this, right? So this is what 2x plus 3 roughly looks like. So this is f of x, right? F of x. And one thing to note is that inverses are actually reflection of functions in the line y equals x, right? So if I draw a line y equals x over here, let's say this is y equals x, the inverse function will actually be a reflection of this. It will be something like this maybe. It will be a reflection, and you can go ahead and plot this, and you can go ahead and plot this, and you will get the same thing, right? And the last thing to note is that since they are a reflection, if f of x is equal to f inverse of x at any point, that is if this graph meets if this line meets this line at any point, it will meet at the line y equals x. This is y equals x, it will meet at the line y equals x, right? And this is about it for the theory part. You could say that I would cover in this video. What we are left with are quadratics, mod functions, and composite functions, right? But the video isn't over. I would like to talk a bit about why why finding inverses like this makes sense, why inverses being a reflection also makes sense. So if you're not interested, go ahead and pause or right over here and maybe jump to the next video. But if you are, then let's talk about it. So first of all, why do we find inverses by making x the subject and then swapping the y's, and why is it such uh, that x y goes to y comma x, right? And I've actually explained this part already, that since you're taking the output and then it gives back the input, hence it is y comma x. So let's talk about why we take inverses like the way we do. So if I have y equals 2x plus 3, right? What we are saying is multiply by 2 and add 3. So if I make x the subject, so for example, let me take an example that when y is 1, when x is 1, y is actually 5, right? So we know that 5 is equal to 2, 1 plus 3, right? If I make x the subject, 5 minus 3 over 2 is equal to 1, right? And this is just a specific case. If I just write y minus 3 over 2 equals x, we know that we're basically saying that what at this value of y, what is the value of x, right? And once I swap the x's and the y's, right, once I end up with an inverse, what I'm saying is that at this output, what is the input, and this new input is actually the output. See if that makes sense, right? So if I take 5, right? If I take y as 5, if I know that output is 5, 5 minus 3 over 2 will actually give me 1. And 1 is actually the input that we took too, right? So if we input 1 into f of x, we will get 5. And if we input 5 into f inverse of x, we will get 1, right? I hope this part makes sense to you, that since this is since we're saying that what is the value of input when this is the output and this is the new output, right? If you don't get this, then it's completely fine. You don't really need to know this, right? And the next part, why are the inverses reflection in the line y equals x, right? So whenever you have 2 points, we know that every point on f of x is going to basically y comma x. Is if there's my alarm again. So basically, if you have x comma y, it will go to y comma x, right? And we know this is happening to every point on the line. And whenever this happens, this is actually reflection in the line y equals x. So for example, if this is 2 comma 5 and this is 5 comma 2, this is the line y equals x, right? So if I just connect these two, so first of all, so the point A is x comma y and point B is y comma x. If you take the gradient of this, it will be y minus x over x minus y, which is -1. And if you're coming from coordinate geometry, you'll realize that this is actually perpendicular, because y equals x has the gradient 1 and this is the gradient -1, right? So we know this is perpendicular. Secondly, if you take the midpoint, for example, I took 5, 2 comma 5 and 5 comma 2 here. Let's check what the midpoint comes out to be. 2 plus 5 over 2, 5 plus 2 over 2, and it comes out to be 7 over 2 and 7 over 2. We know 7 over 2 and 7 over 2 lies on the y equals x line, right? And for generally for any x, for any point x comma y and y comma x, the midpoint would turn out to be x plus y over 2, y plus x over 2, right? And these are both the same number, so we know it lies on the line y equals x. So since it is perpendicular, right? And since the midpoint lies on the line y equals x, we know that this is perpendicular bisector. So basically, this length is equal to this length. Hence, this point is reflected in the line. This point is reflected in this line, and it ends up here. And this happens for every single line there is. Right? So this is the reason why f inverse is actually the reflection in the line y equals x, right? And of course, if they are a reflection, so let's say I have some curve like this, right? And this is y equals x, and then I have some curve. So basically, what reflection basically means is that take this point, whatever this distance is, put it over here, right? And repeat. So when I'm drawing my inverse, it will look something like this. So they will of course meet at the line y equals x, because when this graph meets the line y equals x, the distance from y equals x to this graph is actually 0, right? Hence, when you reflect this, this will also meet there. So f inverse of x and f of x always meet at, if they do meet, they meet at the line y equals x. And just to give you an example from above, we know that f of x was 2x plus 3, and f inverse was x minus 3 over 2. Right? So if we equate these two, what do we get? 4x plus 6, x minus 3, 3x equals negative 9, x equals negative 3. Right? So let's input negative 3 back over there. So 2 minus 3 plus 3 will give us negative 3. So negative 3 comma negative 3, and let's do the same over here. Negative 3 over 2 will also give us negative 3, right? So we see that this has the coordinates negative 3 over 3, and this also has the coordinates negative 3 over 3, negative 3 comma negative 3. So they these two lines, they intersect at the line y equals x when x is negative 3, right? And this is it for now. Bye bye.